So section 4, we're finally getting into acceleration. We've seen velocity describes the rate at which an object changes position. Acceleration describes the rate at which an object changes velocity. So velocity is the rate at which we change position. Acceleration is the rate at which we change velocity. So acceleration is a rate of change as well, but it's the rate of change of velocity. Okay? So the ratio here, change in velocity over change in time, is the rate of change of velocity. And that's our acceleration. So that means that the ratio delta v over delta t is the slope of the velocity versus time graph. Because delta x over delta t is the slope of the position versus time graph. So there's a total correlation here between the two things. Okay? Rate of change of position versus time, rate of change of velocity versus time. We're just talking about velocity now instead of position. Okay? So the definition for acceleration is the rate of change of, this should be velocity. I have lots of typos. It was usually like midnight when I was typing these notes up. So in the x direction is acceleration in the x direction, that's our notation there, equals delta v in the x direction over delta t. So the same would be true for in the y direction. A sub y, acceleration in the y direction, equals change in velocity in the y direction over delta t. And that would be for vertical motion. Pretty straightforward. So remember our equation for velocity in the x direction, delta x over delta t. Same idea, right? Okay, so moving on. A Corvette begins at rest and speeds up to 27 meters per second in 3.6 seconds. So what do we know about Corvettes?
They're only pretty quick, so that's not, they're not gunning it.
They're pretty quick cars, right? This is maybe 50 miles an hour, faster than 50 miles an hour, 60 miles an hour in 3.6 seconds. 0 to 60 in 3.6 seconds, is that pretty fast?
Yeah.
Okay, so this is pretty quick. Calculate the acceleration of the Corvette and discuss the meaning of the units of acceleration. Okay, so I have a delta t and I have at rest. So 0 would be the velocity initial. And at the end of this process, we have a velocity final of 27 meters per second. Okay? So I can calculate my acceleration in the x direction would be delta v in the x direction over delta t. Delta v is the change in velocity, so that would be velocity final minus velocity initial. So vf minus vi over delta t. Vi is 0, so we just have vf on top. So that's 27 meters per second over delta t, which is 3.6 seconds. The meters per second, just showing you one more time, meters per second divided by seconds. We would have to leave it, change it, flip it, and wind up with 1 over seconds like this. Oops. And, yep, I did that right. So then times across, right? This winds up being meters on top. And on the bottom is what?
S squared.
Seconds squared.
Water.
Because seconds times seconds is seconds squared.
We did this in pre-calc earlier this week.
Okay? So now we just got to figure out the 27 divided by 3.6. What's that?
Don't we multiply it now? Huh? You're just saying flip it, change it, flip it.
Leave it, change it, flip it.
Yeah, but now, now you're multiplying it by the top.
7.5 meters over s squared.
Meters per second squared. Those are the correct units. Okay, but now discuss the meaning of the acceleration. What does that mean? So if I don't multiply this out, the best way to understand this is if I don't multiply it out and I leave it as meters per second like this here, meters per second, and then I leave that there per second. So meters per second per second. What does that mean? Because if I have meters per second squared, that is, like, that's the official unit there, but it doesn't explain, like, it's confusing, like, why is that? But if I write it as meters per second, now I can explain what that means. Remember that acceleration is a change in velocity, okay, per unit of time. So here is my change in velocity, and here is my per unit of time, right? So this means for every second that goes by, I'm changing by this many meters per second, okay?
Also, like the graph of the equation.
Like, almost a better way of looking at this would be, let me change colors so I'm not getting confused. Change colors. Okay, so like if I had 10 miles per hour per second instead, just to be using units that we understand. If my acceleration was 10 miles per hour per second, then that means that every second that goes by as I'm accelerating at 10 miles per hour per second, every second that goes by, I'm now going 10 miles per hour faster. So 1 second goes by, I'm going 10 miles per hour. Another second goes by, I'm going 10 miles per hour faster. So now I'm going 20 miles per hour. Another second goes by, I'm going 30 miles per hour now, right? That's how that works. So these units here, meters per second, means every second that goes by, I'm going 7.5 meters per second faster. Okay? Does that make sense?
Yeah.
Okay. When it's simplified, meters per second, in order to do that simplification, we do this process here, meters per second. You put the seconds over 1, you got to leave it, change it, flip it, so now we're multiplying meters per second times 1 over seconds. You multiply across, and you wind up with meters per second squared. So that's how the acceleration unit of meters per second squared comes about. But what does it mean? It means meters per second. And sometimes you'll see it written like this, meters per second. But that gets confusing too. So you try to remember what acceleration actually means. It means you're accelerating at a rate of velocity, meters per second, every second that goes by. Okay?
So it is just,
All right, Lions, capable of very fast, rapid starts. From rest, a lion can sustain an acceleration of 9.5 meters per second squared for up to 1 second. So they can start from rest and get up to speed extremely quickly. How much time does it take for a lion to go from rest to a typical recreational runner's top speed of 10 miles per hour? So you're jogging along in the savannah and a lion is sitting there laying in wait. How long does it take for that lion to get up to your speed as you jog along?
Less than a second.
Yeah. Oh, well, a little bit more than a second, right? So, what do we do?
Convert it from meters per second to miles per hour.
Okay, so our first issue is we have a unit situation here, miles per hour and meters per second squared. So we need to be in the same units. And you're going to see that a lot in this course. Now, the preferred units for us in physics is meters and seconds. So this miles per hour has to go. So our first move is 10 miles per 1 hour. We're going to do a unit conversion on that and turn it into meters per second. Now, we have that conversion.
So in 1 mile, there's 0.4.
You divide-
Actually, we have that conversion straight from miles per hour to meters per second. So I don't even have to do this. I can get rid of that and just go 10 miles per hour over 1 and get rid of the miles per hour and go straight to meters per second. We have that conversion.
Isn't they divided by 2.24 or what?
It's not 3.24.
2.2.
Nope, not that either.
Oh, 0.447
0.447 what?
meters per second.
Meters per second.
In 1 mile per hour.
In 1, there you go. So that's your conversion. So we didn't even have to switch everything. We got straight to the point. So now miles per hour is gone and our units are now meters per second. We can multiply through and we get 10 times 0.447, so what's our result?
4.47.
4.47 meters per second. So that is our, actually, what did we just calculate?
10 miles per hour.
The line is going from rest to 10 miles per hour.
So V.
Velocity.
That's actually our delta V. VI and VF are now there, so we have delta V. Okay, so we want to figure out how much time. We know the delta V, just calculated it, and we're given the acceleration. So a typical physics problem is going to be look at what you have and look at what you're looking for and come up with some formula or a couple of formulas that are going to combine in some way to give you what it is that you're looking for. We are looking for delta t. We have delta v and we're given acceleration a. What is our formula that we're going to use?
EAX.
Yep. Acceleration in the x direction equals delta v over delta t. And this would be delta vx. There you go. Now we're trying to solve for delta t, so that's what we're going to do is solve for delta t. Okay, so first thing I'm going to do is multiply both sides by delta t. So I have a sub x delta t equals delta v x. What? I'm just solving for delta t. Divide both sides by the acceleration. So now I have delta t equals, I'm dividing both sides, so I have delta v sub x over a sub x. So now I have delta t by itself, and I have all of this. I know what delta v is, and I know what acceleration is because it was given to me. So I can plug these numbers in. I have 4.47 meters per second divided by the acceleration, which was given 9.5 meters per second squared.
How do we do that?
Well, we can divide the numbers. What do you get?
0.4705.
0.4705.
26.
Okay, so we write all that down. But we're going to need to go with how many digits for significant figures?
3.
3?
4.47.
Yeah, but
Or is
it's
it
only 2
9.5?
because it's just
Two.
2 on the right side of the
9.5.
decimal, so it'd be just end at
So 2 significant figures? Okay, so 0.47. But now what are the units?
Actually, actually no, is
Seconds.
it, because
It's
of the
just seconds.
9.5, is it only 1?
Meters go away, seconds go away.
Or is it 2 because of the 4.47?
It's 2.
Okay.
Meters go away.
Now, you're right, the meters per second on top and the meters per second on the bottom, those are gone. But this was really meters per second squared
So
on the
there's still a
bottom.
meters per second.
No, the meters are
It's
gone.
just seconds.
Oh, so there's just seconds.
One of these seconds on top with, the seconds on top with one of the seconds on the bottom
So
is
it's
gone.
just 0.47 seconds.
Yeah, it's on the bottom per seconds. So on the bottom per seconds is gonna leave it, change it, flip it to the top and become seconds. So this is 0.47 seconds, which makes sense because we're talking about a delta t, which is time.
So it takes
seconds.
less than half a second.
In less than half a second, that line went from rest, hiding in the bush, to
10 miles an hour.
10 miles an hour and probably tackling you. And that's why lions are, well, one of the reasons why lions are so dangerous. Okay, so the same relationships between position and velocity are true between velocity and acceleration. The slope of the velocity versus time graph, the VT, velocity versus time graph, is equal to the acceleration of the object. So slope of the velocity versus time graph is the acceleration. Just like slope of position versus time graph is velocity, okay? So this figure here is the velocity versus time graph for a car, okay? I see that because of velocity here and time here. Figure B is the acceleration versus time graph, and I see that because of acceleration here and time here. And again, notice how these are stacked. The velocity versus time graph is on top, the acceleration versus time graph is on the bottom, so that key points line up. So we have this lining up here, we have this line up here, we have this lining up here, okay? So during this initial segment right here, we see a linear segment, a constant change in velocity, right? That means the slope of that constant change in velocity, that linear segment, is going to be that constant acceleration. So we should see a horizontal positive segment on the acceleration graph. And we do, it's right here. Whatever that acceleration is. So the slope of that linear segment here is equal to the value on that axis right there. Okay? Then we see this. What's going on in that segment right there?
You have positive
Just
acceleration.
stop.
It's not stop. This is a velocity versus time graph.
Oh, my bad.
You
So
have
that's a
positive
constant
acceleration.
velocity, which means we are not accelerating, right? We've got like the cruise control on in the car. We're not accelerating. So because we're not accelerating, we have we're on the zero on the acceleration curve. Then we have this segment here that has a negative slope to it. It's a constant negative slope because this is a linear segment, which means we're going to be seeing us down here on whatever that slope is. We'll have that value on the y-axis, and will just be a horizontal segment during that time.
So it's just like another position time.
It's just like the position versus time graph, trying to graph the velocity versus time graph. Exactly. Okay? Okay.
So it's just backwards. No.
I don't know if it's backwards.
No,
I
like
don't remember that.
you flip it. So like a position was on top.
Yeah, so now the velocity's on top and the acceleration is on the bottom. Yep. Okay, so we take a look at this one. The particle is moving with the velocity versus time graph. So this is important here. We see velocity versus time graph. At which labeled point is the magnitude of the acceleration the greatest?
The magnitude of the acceleration will probably be C.
You think it's C?
Yeah.
How come?
The lowest.
Oh, no, it's the steepest.
Oh, wait. No, that's the lowest of velocity per second.
So, what do you think the answer is?
C.
Why?
Because it's the steepest out of all the points.
The acceleration is the slope of the velocity versus time graph. So we want, if we're looking for the greatest acceleration, we're looking for the greatest slope. The slope at A would look like that if I drew a little slope on there, right? The slope at B looks more like horizontal, so that's a slope of like 0. The slope at D also looks pretty much horizontal, so that's not going to be it, right? But the slope at C looks negative compared to A, right? But now the question is just which one is actually steeper. So if I erase these marks and we just kind of analyze it visually, which one looks steeper? It looks like C. It's hard to tell for sure. We don't really know for sure, but it does look like C is steeper than A. Okay? And that's what that one's looking for. So my question down at the bottom, does the sign of the acceleration tell whether an object is speeding up or slowing down? What do you think?
It speeds up and then slows down.
Does the sign of it, this is in general, it doesn't have to do with this problem. Does the sign of the acceleration tell whether you are speeding up or slowing down?
Slowing down.
It's a yes or no question.
Yes.
Yes.
The answer is no, it does not.
I have no clue.
Sound acceleration tells whether an object is speeding up or slowing. What's the sign of the acceleration?
Yeah. What?
So either the acceleration is positive or it's negative.
Oh.
Okay.
That doesn't,
It doesn't tell you if you're speeding up or slowing down.
like, it's like a velocity.
So if the velocity is positive and the acceleration is negative, that means we're accelerating in the opposite direction that we're going, and we will be slowing down. If the velocity is negative and the acceleration is still negative, that means we're accelerating in the same direction that we're going, and that means we're speeding up. Okay? So the sign of the acceleration is not dependent on whether we're speeding up or slowing down. It actually is dependent on which way we're going. Okay? Before we're speeding up or slowing down.
That still throws me off because I'm so used to like the negative numbers meaning you're
I
going
know.
backwards, and now you're not going negative. You're just on the left side of your origin.
Or you might be going against what you defined as positive.
Yeah.
Yeah, which is like that's weird to think about.
Yeah. Yep. So if we're going this way, but our acceleration is pulling us backwards, that's going to slow us down. Okay? But if we're going this way and our acceleration is pulling us that way, we're going to speed up. Okay? Does that make sense? So-
kind of like when you brake a car, you're braking a car.
Exactly. Think of it like a car.
Because your velocity, or is it your velocity or your accelerations keep wanting to pull you that way.
Yep.
But your brakes are wanting to stop you, almost pulling you back.
That's exactly what they're doing.
And so
Yep.
it makes you slow down.
Your accelerator is called an accelerator for a reason, and your brake could actually be called a decelerator.
I've heard it called that.
Press
Yeah.
the decelerator button.
Or like with electric cars, they have in the wheels. I don't know how to describe it. Like my uncle bought the Rivian truck,
Uh-huh.
and their auto regen brakes, and so when you let off the pedal, I can't call it gas pedal because it's not. I don't use gas.
Yeah.
But when you let off the pedal, they automatically
Is it like a retarding system? Is that what you're talking about?
kind of where it's like they automatically start reverse pulling the tires, naturally slowing it down.
Yeah.
Which at the same time kind of sends a boost back into your truck. So,
Okay.
So it makes it so your battery lasts longer whenever you.
Nice. Okay, so this is because acceleration is a vector. So the acceleration vector points in the same direction as the velocity vector for an object that is speeding up. And the two vectors will point in opposite directions for an object that is slowing down. And this concept is critically important. You have to understand it, okay? Draw an acceleration vector and a velocity time graph for each velocity diagram below. So we're going to draw an acceleration vector. I'll show you the first one. We have a velocity vector being shown. And also we have dots being shown as time goes on, okay? So which way is the acceleration going here?
Right.
Yes, the velocity is to the right, and we see the dots getting farther and farther apart, which means we are accelerating. So we're speeding up, right? So the acceleration vector is to the right. And remember, when we draw vectors, we got to put an arrow over the top. So that acceleration vector is to the right. Now the velocity versus time graph, v and t, would show us speeding up as time goes on. So the velocity is going to increase. So here is our velocity versus time graph, something like this. Okay, does that make sense? Okay. Now let's take a look at the next one. We see that the velocity is to the left. And if we define positive as to the right, then what is our velocity?
Negative.
Okay, negative velocity.
Positive.
Now, are we speeding up or slowing down?
Slowing down.
We're slowing down. Okay, so which way is the acceleration vector going?
Right.
We're slowing down. The velocity vectors are to the left, which means our acceleration vector has to go against that. So that means we're going acceleration to the right. So now my velocity versus time graph will look like what?
Declining. Opposite of the other one.
What is my velocity, positive or negative?
Negative.
It's a negative velocity, and are we speeding up or slowing down?
Slowing down.
So my velocity starts off big,
Yeah.
but negative, and slows down towards zero. So it does this. Okay? How about the third one?
Speeding up. Oh no, slowing down.
First of all, the velocity vector is pointing to the right, so my velocity is positive, and we are slowing down. So
our acceleration has to go negative.
So which way is negative?
Left.
Okay. Now we can draw the position versus time graph. Not position, sorry, velocity versus time, and I forgot to label this one. So, what does it look like?
It'll start positive and go, it'll start top left and go down.
Yep, starts high because we had a big velocity to begin with, and then it goes towards zero. Okay, and the last one?
We don't have that one.
You don't have that one? What do you mean?
We only have 3.
Really?
Yeah.
Huh, okay. Well, draw it in there.
Don't have room.
Okay.
Our velocity vector is pointing to the
Left.
left, and we are speeding up or slowing down?
Speeding up.
Speeding up, so our acceleration vector therefore is to the, also left, in order for us to speed up. So, there we go.
It's, won't it still look the same way as that first one? Go from the bottom left up to the right?
So velocity is what?
Isn't it going from origin out?
But the velocity is negative.
Yeah, so you go
So
from
is
the
that on
origin.
the opposite side?
Origin down,
Yeah.
because we're speeding up.
There's kind of a pattern.
Wait.
You got it? Okay. And that does it. We're done.